Hi, my name is Matt Holliday and welcome back to my class on Programming in Go. So in this segment I'm going to talk about reflection. I've been hinting at it, we've seen little bits and pieces of it, but now we're going to dive into it a little bit more. We have in Go this notion of the empty interface, and we said the empty interface says nothing. In other words, it has no methods, and therefore it doesn't define any behavior, and therefore it doesn't restrict any behavior, and so in Go it can represent any type in the program. And we've seen that occasionally there are container types, for example, the sync.pool we saw. Well, right now we don't have parametric polymorphism in Go, what most people call generics. And so generics in Go, right at the moment, use the empty interface. And we needed to get data out of that, so we did something that technically is called type assertion, although sometimes I'll call it downcasting, because that's kind of what it's used for in other programming languages. We take some generic thing and we make it be a more specific thing, all right? And the term comes out of inheritance hierarchies, but it's a common term, and I think we can still use it here. So I've got this example, and we're going to have an io.writer. It doesn't have to work only with the empty interface. Okay, we can take other interfaces and ask, do they have something more specific in them? In the particular case on this slide, I'm going to ask, do they have a certain concrete type? So this type assertion uses a bit of weird notation. We have a value or variable, dot, and a type in parentheses. Okay, and what we mean to do is say, hey, take whatever the value is and make it be the thing in parentheses, the type. Now, it may not work. So, and here we've got an example. We're converting it to, we have an io.writer, and we're going to try to convert it either to a concrete type of file or buffer. Now, it's not limited to concrete types. Okay, we can also try to assert that the type is a particular interface, and we'll see that. In this form right here, if it works, f is going to have an object of that type. So in the first case, we're saying, hey, this io.writer, is it actually a file? And the answer is, well, yes, it is, because os.standardout is a file. And so f will be os.standardout, and it will have the type of file pointer. Okay. In the second example, okay, it's not a bytes.buffer. This test will fail. And in this particular way of doing it, it will fail by panicking. Okay. What we're doing when we write it this way is saying we assume it is that type, and if it's not, that's a logic error. Now the thing is, Go gives us another form. Just like we had with maps and other things, there's a two-value type assertion where the second value is a Boolean that tells us whether or not it worked. Okay, so now in this case, the first one gives us the file pointer and true, and the second one gives us a nil pointer and false, and so we don't trap. Now, why is this called reflection? Well, reflection is the notion of a program looking at itself. Okay, in the old days, and this is true for languages like C and a lot of older languages, the compiler knows something about the types in the program. It uses that information to translate the program. The reason for having types was to translate it in a way that was reasonably correct and find certain kinds of errors. And once the program is converted to machine code, the object code that we used to actually run, all that type information was lost. Okay? Reflection is the notion that when the program is done being compiled, the compiler can leave behind type information in the executable. The same way we get, for example, literal strings, right? If I go look at the executable for a Go program, a literal string will appear in the executable, in the binary. Well, now we're going to have a bunch of type information in the binary, and we have utilities in Go that allow us to look at that type information to say, hey, here's a type, give me some stuff about it. Okay, one way we can use that is we can actually directly call the reflect package. There's a function there, for example, deep equal, that uses reflection to try to find equality between structs that may not otherwise be comparable. If I look at my struct definition here for want, it has an embedded slice. And we know the slices can't be compared with the equal operator. But if I call reflect.deepEqual down here, I can actually use reflection to go in and look at the type and check all the way down Is it actually equal? Is the string the same? Is the byte slice the same? Does it have the same things in it? Now, reflect is also used by the standard library on itself. You're going to see reflection in a lot of places. It's used in JSON decoding, and it's used in printing. So now I'm going to actually go back one slide to the one I skipped over, because I want to look at the implementation of println and another feature that uses reflection, and it's called switching on type. Okay, we had a switch statement where we looked at a variable and asked, does a certain value match? Now we can have a switch statement where we ask the type of the value, and the cases are other types. Does this type match? Okay, and this is actually what happens inside println. Because if you think about it, if I'm going to print a variable, okay, if it's a string, well, I can just take the bytes of the string and shove them in the output. And if it's a stringer, I can just call the string method, get the string, and do the same thing. I don't have to do any more work. And those are the first couple cases. All right. Again, a switch statement for types works like a switch statement for values. It's top down. Okay. And presumably there's a default somewhere. I'm just showing a couple cases. So again, we're looking at whatever this value is. And again, we have a variable argument list of empty interfaces. So we just start looping over it. Okay. And we look at the first one and say, well, is it a certain type? And the case is here, it's a string. All right. If it is, we'll just put the string out. And again, we're using another kind of unpacking, unpack the string into the byte buffer. Okay. As I said, it doesn't have to be a concrete type. So the very next case says it is a stringer. And again, this routine lives in package fumped. So there's no fump.stringer in front of this because stringer is in the package fumped. Right? It goes and looks and says it is a stringer. If it is, then we know it has a string method, call it, unpack the results into the byte buffer. Now, the other thing going on here is we have in the middle of this an assignment, right? We have, right, a short declaration, I'm sorry, and A takes on a value of the type of the case if the case has an individual type. So if there's a single type in my case, then A is a value of that type. So that's why I can go ahead and call A.string, because in the case for stringer, A is a stringer. In the case for string, A has been asserted to be of type string successfully. Okay. There's an example in the textbook where they show a case with two types, and when that happens, since the two types, it can't be both of the types at the same time, then it's still just an empty interface. But if you have a single type in your case, then that variable A becomes a value of the specific type in that specific case. So I'm going to go into the playground in just a second, and we're going to look at an example. I'm going to talk about it on this slide. Okay. There's a particular style of doing JSON where you might have, for example, some sort of item that has a type, and then based on what that value is, you have a key field of that type with some more data. Now, I think that's an inconvenient way to do JSON, but some people do. And the question is, well, how can we decode this? Now, there's more than one way, but I'm going to show you a particular way because it allows me to use reflection and allows me to show how to build a custom JSON unmarshal method. I'm going to start with this response wrapper type, and I've got two things. I've got the actual response that I want to fill in, and then I've got the response wrapper, which embeds a response. And I'm going to explain why in a second. We have to do that because when we create a custom method for unmarshaling, it can't be recursive. We can't call a custom method on unmarshal that then tries to unmarshal the same thing because it'll just call back into that custom method and we'll get trapped. Let's move into the playground. Okay, I have the type here, and what I have is the data that I showed in the slide, and I have a little program that's going to take a couple of these values and unmarshal them and print them out. Okay, fine. Now, first of all, if I do it right now, it's not going to work right because my type here, I want to get these various values, you know, the album, title, artist, but I haven't done it with various structures. Now, there's a way I could probably do this with a bunch of different structures for the different keys. I'm not going to do that. I'm going to demonstrate something else. Right? So it doesn't work right now, and the reason what it needs to work is a function that I haven't written yet, but I'm going to write it. Okay. You know what? We're going to put it down at the bottom just because that'll make it easier to see. Okay, so I'm going to come down to the bottom and start writing this. And what I need is a function on a response wrapper, a method, excuse me, on a response writer. And again, typing in front of the camera is really hard. So I need to, it's going to have to be called unmarshal JSON. Okay, we saw already that we have these methods JSON.marshal and JSON.unmarshal. Okay, but when I want to have a custom unmarshaler for a type, I need to call it unmarshal JSON. And if I do that, and of course it's going to take an error, it's going to return an error, I'm sorry. Okay, and what it has to take is a byte string. Now I'm going to do one more thing. I'm going to name my error return value so I can use it as a local variable inside the function for convenience. Now, there's a couple of choices here. I can unmarshal JSON into a struct, but I have another option that goes JSON allows me to do, and I'm going to show that. We're going to have a type, which is a map of string to interface. Okay, and that can represent any JSON object, because a map of string to interface, right, the strings are the properties of the JSON object, and the empty interface is the actual value of whatever it is, okay, of any type. And I'm going to go ahead and again, I don't know, how do I ever supposed to type in front of a camera? All right. Now, this first thing I'm going to do, and I'm just going to make a comment here. I'm ignoring errors for the second. So the first thing I'm going to do is I'm going to unmarshal into the response. Now, the only thing it's going to unmarshal is the item, because that's the only one I put a JSON tag on. Okay, it's not going to find the other anything else because they're all capital names and my data has lowercase. Now, there's another alternative. I could be even more explicit about that and do this. And if I did this, I'd be actually saying to JSON, don't decode this field. Okay? Or I can make them all lowercase, but I don't want to do that. All right. Anyway, it's only going to unmarshal the value of item, and that's fine. Now I'm going to do this same thing again. So I'm going to call it twice. And again, I am skipping the error handling. All right. The second time I unmarshal it, it's going to give me this map of string to interface. And I'm going to go fishing inside that based on the type of the item. So what I want to do now is switch on r.item and look at some cases. Okay. So the first case is, and I'm only going to do a couple of these, is the case where it says album. All right? And I'm going to do some work, and then I have the other one I'm going to do song. All right? So if the item is, in fact, an album, I want to go and get album data out of it. So I'm going to go into my map of string to interface and try to get out album. And that's also an object type. So I'm going to try to force it to be another map of string to interface. And if that works, I'm going to do something with it. All right? Well, the next thing I need to do is I need to get out the title of the album. If we go back and look at the data, right? So the album had an album and a title. It might have other things. I'm not showing them here. Right? So now I have to go and get the album. And what I'm doing is I'm going inside the object I just had. So I went into my top level map, got the key for album, and if that worked, I'm going to go into the data that that represents, because that's another object, a map of string to interface, and try to get a string. And if that worked, okay, then I'm going to put that into my eventual type, right? Because what I'm doing is taking this kind of data that's here in like J1 and forcing it to end up in this response, okay? So my response, I have the item, I'm going to fill in the other things. In this case, I'm going to just fill in the title. I'm going to stop there, right? So again, if I had an item as the type, excuse me, my item was of type album, all right? I went and found the data for the key in this map of string to interface, which gave me another map of string to interface. And if I find a title in it, then I'm going to put that title into R, okay, which is my response wrapper, but it embeds a response. So I'm really setting the album field in the response. Right. Now I can do much the same thing for song, right? Just copy this, except now I'm looking up song. And if that worked, right? Well, now I need to go inside and look for things inside that. Right? Now I'm going to look for title and artist. So now if I run this, if I go back and look at my main program, right, I'm going to unmarshal these sample data into response wrappers. It's going to call my custom unmarshal method, which is just going to unmarshal the data once to get the item into the structure, and then unmarshal it a second time into the map, and then I'll use reflection to go poke around in the map until I get what I want. All right. And when I run that, I actually end up getting these two structs, right? The first one says the item is in the album, and then I have a value for the album name, and title and artist are blank. For the second one, I had a song, the album is empty, but I have the values of the title and artist, okay? And I did that by using type assertions as I poked around in this map of string to interface. I'm going to work through a second example that's very similar. Again, we're going to go poking around in JSON. We're going to do a different kind of function, one that I found useful in certain kinds of unit tests. Right? I have some JSON that I got back from doing a query. And what I want to know is there some piece within it? I want to see if there's a subset of data inside this other data. And I may not want to decode the whole thing. I'm just looking for this particular thing. All right, and so I found an effective way to do it with reflection. And here's an example of a function. We're going to work on this in just a second, where I go into my exploded map of string to interface and start poking around to see if the key is in there and to see whether or not it has the particular type, and if it does, whether or not the value matches. So in the playground, I've got a unit test, and the playground can run unit tests. All right, and we're going to go looking for some things. I've got a piece of unknown data with some stuff in it and some possible sub-pieces. And what I'm going to do is I'm going to go run around through this data and call something called check data. And check data is just going to unmarshal what we want and what we've got, and then call my function contains, which I haven't really written yet, right? So if I run this right now, my unit tests fail because contain says, hey, that's not implemented. And in fact, that's what happens. If I run it, all of my tests fail, not implemented. Right? So we need to implement contains. And in order to do that, we have to have some other functions, right? And so one of these is going to be this match. All right, we're going to go looking for a key. It has an expected float 64 value. The way generically that JSON encodes numbers is as a floating point number, and that's how they get decoded if you don't do something else. Okay, so when we decode a number, it may look like an integer. It'll get returned to us as a float. And then I have the data, which is my map of string to interface that I'm going to go looking in. And we'll just return true if it matches. Okay, so what we're asking is, does this data have in it a certain key with a certain value of type float? All right. So the first thing we do, of course, is we use our standard way of looking at a map to ask, does the map have that data? And I don't normally indent everything, but I'm going to do it now just for convenience. And I'm going to return false if we don't find it. Okay, so the first question is the key there? And the second thing I have to do is I have to do type assertion to say, is the key a float 64? So if it is, OK is true, and the value I just got by doing my type assertion is equal to the expected value. Now, you may know from working with floats that equality is not always a safe thing. These are all going to be integers. That's going to work. You might want to be a little bit careful if they really were floating point numbers. Okay. We don't normally test for equality. What we do is we test to see if the difference is smaller than some teeny weeny bit. All right, because we know floating point numbers are not always exact. Anyway, we'll be dealing with integers right now, and so if this all works, we'll return true. All right, and what this says is the key is there in the map, it has data, the data is a floating point number, and it matches the floating point number we passed in. We can do exactly the same thing with a string, so I can actually copy and paste this. So I've created a copy of match string, or match num, called it match string, and we're going to do the same thing, except I need to pass the expected value as a string. All right, so the key and the expected value as a strings. I need to extract it as a string, and instead of doing a direct comparison, I'll do a case-insensitive comparison. Okay, so now I have a way to match a number or a string. I could do it for some other types. That's good enough for right now to prove the point. Okay, so now I'm ready to start building contains. All right. So what contain says is my expected data to be found within the data that I'm passing in? And that's a little more involved. So we're going to loop over, all right, the expected data. And now we're going to use a type switch. So the first thing I'm going to do, I'm going to define this local variable x to be v of some type based on some type cases. And in the first one, of course, is going to be case float 64. Right? And we're going to use our match num. Right? So we're going to say, hey, does it match if I pass into you k? Well, k was the key for the expected data, right? And b was the value which we've now converted into x. So x is not just an empty interface now. X is a floating point number that I hope to match with this key, right? And of course the answer is if it's not, then we'll return an error. And right now we're assuming we're going to deal with integers, so I'm just going to cast that. Not very good for real stuff, but good enough for this example right now. All right. And if I want to do this for the string, well, it's exactly the same thing. All right. I put string here, and so now x will be a string type, and that's fine, except I'm going to want to change this and not cast as an int. All right. So again, and I need to actually call match string, sorry. All right. So if it's a number, I'm going to use my matching number method. If it's a string, I'll use that. So the third case I got to deal with, and remember, these cases are about the cases in the expected data. First, I was looking to see, hey, I have an expectation of finding a number, then I have an expectation of finding a string. What if I expect to find an object? So my third case is the case of a map string interface. All right, a map of string to empty interface. All right, that's the data I'm looking for. So now I've got to ask, do I have that key? And if I don't, then it's an error. All right, the key is just missing. Okay, and I'm going to do this a little compactly. I'm going to have an else if, all right, And the else if is going to be the case of the key is there and it is a map of string to interface that I can go look at. And the last case is the key was there, but it was the wrong type. Okay, and I'm just going to go and print that out real quick. Okay, so what if the key is there? Well, what I need to do now is I need to, right here in the middle, is extract a map of string to interface from my unknown data, right? And if that worked, okay, well then I need to look inside of it. And this is where we do contains recursively. Okay. We're going to take our X, which is the unknown map of string to interface, and pass that whole thing into contains again. And if that finds what it's supposed to find, good. All right. And we're only doing this if we could actually downcast it to a map of string to interface. And if not, then we have this other case where the internal data didn't match. And again, we're doing the contains because we can't just do a comparison. And we don't want to do a reflect deep equal because we don't want the complete equality. What we're just trying to figure out is, does this fragment exist? And that's why we had to write our own contains. We couldn't use deep equal. Okay. And now, okay, so this is contains, right? And I forgot to say, hey, if all of that didn't cause an error, return nil because there's no error. And now it all passes. Okay, there's no way, unfortunately, in the playground for me to show it verbosely, but the test passes. In other words, if I go look at my little test cases, right, can I find ID 1 inside this unknown? And the answer is it's right there. How about extra as the value 21.1? Okay, yeah, I'm using a floating point number. I'm just getting lucky. All right, and so on, these other things. And here's a case where I'm actually looking for the address, but I'm only checking to see if the street and city match, so I didn't even match the zip. And here's why I'm using contains and not trying to use, for example, deep equal. All right, because I only want to see, I just want to see if certain pieces are there and not does it completely match, which is a different thing. All right, so that's a quick introduction to the reflect package, okay, which we only showed in one case actually using reflect directly. That's the example of a unit test that did reflect.deep equal. But if we look at type assertions or type switching on type, that's also all doing reflection. It's going into the type information that the compiler saved in the program and using that to ask questions about, well, what is this thing really?